and when the light strikes with the atoms, so the here light we are talking about X-rays. So when X-rays strike with the atoms, so diffraction occurs. And how does that diffraction occurs? That diffraction occurs due to the electronic cloud. We know that in atom there are electrons that are orbiting around the nucleus. So when X-ray is coming towards the material, so it will penetrate inside the material, because X-rays will have a higher frequencies. As you will see the electromagnetic spectrum, yeah, so here if you will see the electromagnetic spectrum, so X-rays are the one which is having highest frequency, although the gamma rays have highest frequency, and the X-rays will have a frequency less than the gamma rays, but still the wavelength which is having higher frequency means that will have higher energy. So higher energy allows them to penetrate into the material. So when they penetrate into the material, they come in close interactions with the atom will have electrons surrounding it. So those electrons will act as a hindrance, and from those electrons the diffraction will occur. So the incoming X-ray will get diffracted, or in simple way, if you want to simplify this word diffraction, so you can say that the wave or the X-ray is getting reflected. Although this phenomena is not a reflection, but it can be considered similar to the reflection. So from those atoms, from those electrons, the X-ray is getting reflected in different directions. So in case of Miller indices of planes, you have seen that there is a there are different type of planes, like you can mark them as, there are this one plane, 0, 0, 1 plane, or there are different type of planes you can draw in a cubic crystal structure. So if we have to visualize them in 2D crystal lattice, so you can make a plane like by this vertical straight lines, or you can also consider these as the planes, or you can also mark planes likewise shown in this figure, and you can also make planes by this horizontal direction. So what actually a plane is? So if you hold a thin sheet of paper, or if you hold a paper in your hand, so that sheet of paper, you can consider that sheet of a paper as plane. And when you hold that piece of paper or that A4 sheet in your paper in your hand at different angles, so that can be visualized as a plane in a cubic crystal lattice having different orientations. So at a point we can have infinite number of planes, and if you have this crystal system, means I have placed these points, these dark gray points in a 2D sheet. So on these points you can have different type of crystal planes. Likewise, you can draw different type of lines in these points, and those all lines will mark as the planes. And these X-rays which will be striking the material will get reflected from these atoms which are placed which are there in this crystal lattice, and that diffraction will lead to constructive and destructive interference, and those constructive and destructive interference will tell us about the plane from which that is the wave is getting reflected. So you will think that how incoming X-rays will get diffracted from all these type of planes. So the phenomena is that if this is the incoming X-rays, and if this is your sample, this whole thing is if your sample, then this incoming X-rays, if this is the source, so this source is rotating. X-ray source is rotating. So when this X-ray source is rotating, so X-rays will fall from different directions on this crystal lattice. So that is why the X-rays will get diffracted from different planes. So this is the constructive and destructive interference. Means constructive means they are getting added up. Different these X-rays are getting added up. And their magnitude is increasing, and in destructive they are getting cancelled out. So applications of XRD. It can be used for structure of crystals, means to determine what is the structure of a crystal, in the determination of crystal parameters. So structure of crystal, likewise, whether it is a BCC, FCC, these structures can be determined. And what are the crystal parameters? Crystal parameters, you have heard about the lattice parameter like A, B, C. Likewise, if we have a cubic structure, this ABC will be different. If you have a tetragonal structure, so in tetragonal structure will be like this. Means the C, A and B sides will be of equal length, but C side will not be equal. Means here A is equal to B, and is not equal to C. So this is the case of a tetragonal. But if you will take the case of this cubic crystal structure, so in cubic crystal structure, these A, B sides will be equal. A, B and C sides will be equal. So these parameters, that what are the dimensions of what are the quantitative number of A, B or C, that can be determined from the XRD. And observation of any crystal change, that sometime if you take the example of SiO2, silicon dioxide, so silicon dioxide also exists in amorphous form and also in the crystalline form. So crystalline form means they have a periodic arrangement throughout, and in amorphous means those atoms are randomly oriented. So that amorphous and crystalline phase can be differentiated with the help of XRD, and they can be used in the identification of crystalline minerals. And there are also minerals, means likewise SiO2, this simple silica or sand which we call, that is also a type of mineral. And likewise, when scientists discover different materials, so these XRD can be performed on that, and their complex structures will be known, and their crystal structures can be found out. And quantification of amorphous phase, means some material will have a crystalline nature as well as some traces of amorphous nature. Means some amorphous nature is also present in a crystalline material. So how much amorphous nature is present in a crystalline material, that will also get reflected from the XRD. So these are the these points basically refers from the research perspective. People who generally perform their have the research area pertaining to XRD, they go into these particular directions. But you need not to worry about this. You just need to remember that you can determine crystal structure, you can determine lattice parameters, you can determine whether the material is amorphous or crystalline, and if there is any phase change in the material. So those are the things which we will expect from you in from your learning experience in XRD. So we have learned about diffraction. So in diffraction, actually, the diffraction gratings must have spacing comparable to the wavelength of diffracted radiations. So you have also performed a slit experiment. If you know that if there is a small slit and some wave is coming out, some wave is incoming wave strikes this slit which has this narrow space. So from that space the wave will get diffracted. So in case of diffraction to occur, The diffraction grating or this space must be comparable to the wavelength of the diffracted radiation. Means if you have, suppose this slit I have, and if some wave is coming out, I'm sending a wave from here. So if the wavelength of this wave is comparable, means it should be comparable, means equivalent to the size of this hole. If it is comparable to the size of this hole, then only this diffraction will occur. Okay, so now this is the slit experiment. Now let us move to the at the microscopic level, means in terms of atoms. So we know that atoms are arranged in a material, in a crystalline material. They are placed closer to one another. So this is the interatomic distance. So now this interatomic distance, or the distance between the atoms, will be considered as a gap from which the diffraction will occur, and this gap is comparable to the wavelength of X-rays, because in the electromagnetic spectrum, if you will see, the wavelength of X-rays varies from 1 micrometer, this is 1, to 0.01 nanometer, and this is the range in which the interatomic distance lies. So that is why we use this X-rays, because the interatomic distance is approximately equal to the wavelength of X-rays. So I hope it is clear to you. Now, X-rays was first discovered by a German physicist. His name was Max von Laue, and he lived from 1879 to 1960. So you can see in 1960 this technique was invented, and it is over 60 years that people are still doing research in it. And he was awarded as the Nobel Prize in 1920 for this. So in his experiment, how he had generated these these X-rays, we can see there is a filament here. This is the filament. Filament means likewise we use heater in our home. In winters we generally use heater, and that heater has a coil, and you heat when you switch on the heater, that coil gets heated up. So similar type of coil is used here, and when you heat that filament, and how that heating of the filament occurs, by supplying electricity to that. And when you supply a very high voltage of electricity, then this filament get heated, and it is heated up to that temperature that it ejects electrons. So these are the electron beam, or electrons which are ejected from this filament when they strike a target means here tungsten metal is placed. When these fast moving electrons strike the tungsten metal, then they emit X-rays. So in this way he has generated the X-rays, and he has used the X-rays in case of zinc sulfide. So what he has done, that he has generated the X-rays, he made them fall on a single crystal. This is the single crystal, means zinc sulfide crystal he has used, and this is a photographic plate. Photographic plate means in old days, generally now we see results on our computer screen, but in the older days these photographic plates were used. So these X-rays which are coming from this crystal, they have been projected on this photographic plate, and they have shown a very beautiful pattern. Likewise, pattern like this, and likewise here it represents there's a nucleus, and here these are some of the electrons and atoms which are situated out there. So in this way he has performed his basic experiments of XRD. And how does it work? So I've shown you this in first lecture also, but today we are going in some details. So this is the X-ray source, this is the sample. The X-rays is falling on the sample, and this X-ray source is rotating. That is why these X-rays will get diffracted from different planes. So this thing you should keep in mind, that how the X-rays will get diffracted from different planes, because this X-ray source is moving, and a material has atoms arranged in a particular fashion, and all these atoms will have different planes surrounding them. So this is the detector, and this is how this actual machine will look like. So this is your sample source. Here is your sample. Here incoming X-rays are coming. It is diffracted. It is detected by this detector, and these detectors are moving in a circular fashion. So the heart of this X-ray, or the main thing from which the or the main you can say the mm, main point from which you can learn the X-rays in a very good way is the Bragg's law, and this was named after this father-son duo. And this left-hand side picture is the picture of Sir William Henry Bragg, and on the right side is Lawrence Bragg. So these are the father and son. Those were working on this X-ray diffraction. So generally, this father was experimentalist, and his son made the mathematical calculations of the experiments which his father has performed. So in the history, there's only one such example where father and son has received a Nobel Prize in X-rays. So I'm showing you some history also, so that it creates interest and it will help you to know this technique in a better fashion. So this was all about it, and they have received the Nobel Prize for it. And there's a very interesting fact that on the X-rays also only, there are number of these Nobel Prize which is have given from 1901 to 1985. You can see this much of Nobel Prizes related to the X-rays have been awarded by the committee so far. So now, so here is the incident beam. This is our sample. And so this is a sample which you want to know about. So you have incident beam, means X-ray beam, and it should go in a straight line, and it should follow the path of a transmitted beam. Means if there is no sample in between, then this X-rays or this black beam will follow a straight path. But what will happen? It will get diffracted, and it will not get diffracted in one direction. It will get diffracted in different directions. So this is a very important slide. So please look at it carefully. So incident beam, it should be transmitted in a single direction, but it is getting diffracted, and it is getting diffracted in different directions. So how is it is getting diffracted? So this you will see. We will consider this particular direction. So this is our sample. So in sample, actually there are different planes. I have only shown these planes, and these blue lines marks the planes, but so you can see there are different planes in this sample, and when the incident beam is striking this particular plane, it will get diffracted in a different direction, in a particular direction. So the Bragg's law can be understood in two part. That he stated that for every diffracted beam, there will exist a set of crystal lattice plane such that diffracted beam appears to be specularly reflected. Means if I will consider any diffracted beam, suppose I will consider this diffracted beam, then suppose this diffracted beam, then for this diffracted beam also there will be a particular set of planes. Suppose this is this plane from which it will get diffracted, and it will appear as a reflected beam. So what I wanted to convey here is that the diffracted beam will appear as a reflected beam, and that reflection will occur from a particular set of plane. This Bragg has understood from his experiments that this diffraction in different directions is due to the different planes which are there in the sample. So now consider this figure. So we have a crystal lattice or with these atoms which are placed in a material in a particular fashion. This is the X-ray. It is striking this atom, suppose. Now it will get diffracted in different directions. It will get diffracted in different direction because as the sample is rotating, the X-rays will also fall in this direction, in this direction, in this direction, and they will get diffracted. So, let us keep it simple. So we have this X-rays incoming ray. This is the transmitted beam, and these are the diffracted one. So these phenomena will happen in all set of atoms. Here I am showing only this one way because to keep this picture neat and clean. Otherwise, these on all these atoms, these X-rays will be fall. These X-rays will be falling. So this diffraction will occur in this particular set of planes if this is the incoming X-rays. So this is the X-rays here. Now, suppose I'm considering this as the diffracted beam or reflected beam, whatever you want to call it, but it is better if you call it as a diffracted beam. Means it is getting diffracted in all directions, but I'm considering this blue direction only. Then for this blue direction, I'm marking it, showing it by a longer arrow, means it gives the resultant of all these arrows. Means in this direction, this longer arrow shows that all these diffracted beams shown by this blue color are pointing in this particular direction. So now from it means that for this blue diffracted beam, there is a particular set of plane which is shown by this blue line. Means this is a plane. This is the plane for the blue diffracted beam. Now suppose there is another diffracted beam. Suppose now I'm considering a different direction, which is this red, which is shown by this red color arrow. So now for this particular diffracted beam, there will also be a different plane, because from one particular set of plane, there will be only one particular direction in which the beam will diffracted. Means suppose what I want to say here that this is a material. Suppose it is a reflective material. So if your beam is coming in this direction, then it will get reflected in this direction. Okay. Now suppose if I'm changing the angle of incidence, suppose it is, this was 1, this is 2. Now this is the second incident wave. Although your this material, reflective material is same, but you have changed the angle of incidence. Now this reflected beam will follow a different path. So this is the 2 dash reflected, this is 1 dash. So this is what I wanted to show you here from this figure also, that for the red arrows, there will be a different set of planes from which it will appear to be specularly reflected. And for this, suppose maybe these are the planes from which it is appearing to be reflected. So this was the first idea which was given by the Bragg, that when X-ray interact with the material, it get diffracted, and diffraction occurs due to different set of planes. So this is the first law which is shown here. Means this is the incident ray and this is the reflected ray, which this picture I have already drawn, that if you change the angle of incidence, angle of reflection will be changed. Now in the second part, he considered that suppose this is one plane, this is another plane, and the distance between these two planes is t. Then he formulated a formula which gives a equation which is n lambda is equal to 2d sine theta, where n represents the order of diffraction. So we'll see what is the order of diffraction here. So here lambda is the wavelength of X-rays, which is generally known to us. DHK, this is the interatomic, this is the distance between the planes, and sine theta, this is theta is the angle of incidence. So this is the important part of this X-ray diffraction, and which is mostly asked in exam, that what is Bragg's law, and you will be asked about its derivation. So this is how we will determine the Bragg's law. So consider atoms. So this is one plane, these are the atoms, or you can consider it as a 2D lattice, because in 3 dimension it is difficult to show. So on a sheet of paper, we show it in the form of a 2D lattice, and these circles represents atoms, and these are the X-rays. So X-rays are, so this is the first incident X-ray, this is the second incident X-ray. So you will be thinking that if there is only one source, how come I am showing these two? This is the source. How come I am showing this incident ray 1 and 2 differently? Because the source is moving. That is why at one particular instant it was at this point, in another particular instant it was at this point. So these X-rays, these are striking the material, and when they are coming in contact with this material or these atoms, they will get diffracted, or you can say they are getting reflected. So this incident beam 1 is reflected from this point A, whereas incident beam 2 is reflected from point B. And as you can see, if they are in phase, means if they are in phase, there will be constructive interference, and you will have an increase in magnitude. And if there is a, if they are out of phase, you will have destructive interference, and you will have zero magnitude. And here you can see they are not exactly in phase. They are there is some distance, they are out of phase by some distance. So here the effective amplitude will be not this much high. Their effective amplitude is somewhat smaller than this, but larger than these individual waves. So it is not always that it will show a zero and the maximum result. Maximum means it will not show a zero and maximum result always. It can show a maximum, a zero, as well as a value in between, because of the phase shifts which is present in between these incident rays. So now here is here is what we have to majorly look at. So here you can see you can draw a perpendicular from A to C and A to D. So these are the so these perpendicular will form a right angle triangle. One triangle is this ACB, another is ABD, and it is very simple trigonometry which you have to use. And when this incident X-ray is striking the material surface at angle of theta, this is the incident angle, and similarly this is the refracted angle. And if you will see by geometry, then this angle will also be equal to theta. You can find out that how it is equal to theta, and if you're not able to find it, I have shown it in the next slide also for your convenience. So now this is the path difference, this C, B, D. You can see if you will measure the length of these lines, then you can see that incident ray 2 has to travel a larger distance in comparison to incident ray 1. And how much extra distance incident ray 2 has to travel? It has to travel a distance of CBD. So are you guys getting it? Is there any difficulty?
No, sir.
Okay.
No, sir.
So means for this incident ray 1 and incident ray 2, the wave 2 has to travel a larger distance, which is equal to the CBD length. Means this, if you add the CB plus BD, this will represent the extra distance which has to be traveled by these waves, and this should be equal to the n lambda. And why it is equal to the n lambda? uh, Let me show you. Yeah, so you can see now this figure, that this extra distance, if you have to see this extra distance, suppose this is point 1, 2 and 3. This extra distance means 1 to 2, 3. This extra distance will be equal to, this is a distance means 1 to 2, 1 to 3. This distance will be, if you have to measure this distance, you can just add the wavelengths. You can add the wavelengths, because these are the rays which are going from these points. Yeah, so if you will add these wavelengths lambda, then you will get this distance. So here you can see this is one trough. Let me change the color. So this is the one trough, means the bottom side of the wave. This is the another. So this is one wavelength. Okay, so this is one wavelength means lambda. Now this is, if you will see this distance, this is half lambda. This is half lambda. And if you will see this also, this is also half of the wavelength. This is another half lambda. So if you will consider, if you will add it, you will get 2 lambda. And in generalized case, we can write it as n lambda, because n will vary. N will vary because if this first wave is interacting with the third wave, which is getting reflected from another plane, suppose, so this is an important point, because nobody teaches this point and everybody gets confused that why we are writing this path distance is equal to n lambda, because we are measuring the path distance in terms of the wavelength, and where you can add this wavelength, then you will get a multiple of a, because of wavelength of x-rays is fixed. How many wavelengths are there in this particular distance, that you can find out by having an integer n. So suppose there is another plane here, this is a third plane here, and if there's another wave which is getting reflected from this point, suppose, and it has to interact with the wave 1. Suppose this is 1, this is 2, this is 3. Now suppose 1 and 3 are interacting with each other, then obviously this distance, this extra distance for the wave 3 will be different than the wave 2, and the n will be changed here. So this is what I wanted to convey from this. So we have to write that this extra distance is n lambda. Okay, now this CB is, you can use simple trigonometry and you can find out the CB, because the opposite to this vertex angle, this will be the perpendicular, and you can write this distance CB in the form of sine theta. Sine theta is perpendicular over hypotenuse. So this is the DHKL. We have DHKL means sine theta is equal to DHKL over this sine theta will be equal to CB over DHKL, means simply sine theta, if you have to write, how you can write it, you can write it as CB perpendicular over hypotenuse DHKL. And what is DHKL? Here DHKL, I have told you that it is the interatomic distance. So if you will see this distance, this one, this is equal to DHKL. So this we know, and this is the perpendicular. Sine theta we can find out, this is DHKL, and CB you can find out it from here, and similarly you can find out BD. and you write it in this form. You can add it and you will get this beautiful formula, which is 2D HKL is equal to sine theta. And it is a very basic formula in the this X-ray diffraction or in material science. So this is a generally very basic question which will be asked if you are dealing anything related to the material science. So this is how we can derive the Bragg's law. And yeah, so we have derived this equation, which is equal to n lambda is equal to 2d sine theta. So what does this actually means? Means although we have derived the equation, what this equation tell us? So this equation tell us the possibility of constructive interference, that how that when the interference will be constructive, that can be determined from this Bragg's law. So yeah, this slide generally shows you that this was the incident beam one, this is second. So this was the incident angle theta. How come this incident angle theta is equal to this angle? Means this angle. So if you're not able to find it out, then this slide will definitely help you to get it done, that how come this angle is equal to this theta angle is equal to this theta angle. So this is again the same thing which we have seen earlier. So this is how a typical XRD machine looks like in research labs or institutes which perform research on the X-rays. So here in this XRD, you just need to remember the basic principles, this Bragg's law. You don't need to worry about much of it's that the parts of this X-ray machine. You just simply remember this, its geometry, that how this sample, incident, beam and detector is placed. That will be suffice for you. And this is these are how the peaks in a crystalline material and in amorphous material looks like. So if you perform X-ray XRD experiment, then this is what you will get from on your computer screen. This data you will get, and this data will be compared with the available data, and you can mark that okay, this is the 1 1 plane, this is the 1 1 2 plane, and based on these planes you can find out the crystal structure. So I think this is suffice for today. In the next class, we will discuss some of the advantages, what are the limitations of this XRD technique, and most importantly, we will see that how this Bragg law, which we have studied, can be used to find out a particular find out the lattice parameters if we have the information about the planes of a particular system. So this was all for today, and